Hello everyone. In this video we are going to talk about the control method called the computed torque, but applied in a decentralized or independent joint control manner. So here we still assume that the gearbox ratios are large, the robot does not move fast, and we can control each joint independently from the others. And the effect of the motion of others, we still consider it as a disturbance, but this time different from the previous video where we tried to use a PD or a PID compensator only. This time we try to bring in an extra term that kind of tries to cancel the effect of that disturbance. We try to estimate that disturbance and add it as an extra input to the control system, okay? And that extra input that we calculate and we pass to the system, that's the reason we call it the method of computed torque. And the goal of that is to cancel, as I said, the dk that we had. Now we try to add the dd term. So that's why we call it computed torque. And also this computed torque method also needs another extra element that you add to your feedback system. So in the past we only had the feedback, let's say a PD controller. Now we have something that is not using the information from Q, so you don't use the feedback from Q. You directly use this block coming from the desired Q. So this extra block, which here is shown with this block F, we call it feed forward. So this time your control algorithm is feedback, which is shown with block H, plus feed forward, which is shown with block F. Okay. So let me, for that reason, let me first talk about the feed forward. So here we assume that we have the system to be controlled is G, so G is your robot. H is, let's say, a PD or a PID controller or anything. And F is the feed forward control or block. If I want to calculate the error here, it is going to be the input minus the output. And for the output Y, it's going to be G times this signal. Whatever the signal is, G times that is Y. And what is that signal? Well, in this case, that signal is F times R plus H times E, correct? Because if you look, this is R. So it's R times F that goes here. And then you have what? This signal here itself is error. The difference, this is error. So error times H. So this guy is H times E. Right? So R times F plus H times E is this signal, which is multiplied by G to get you Y. So now if you rearrange this and find E as a function of what? As a function of the other blocks, you clearly can see that the error here is going to be 1 minus GF divided by 1 plus GH. Now, if you can choose your F to be the reciprocal of G. So here we choose our feed forward block to be reciprocal of G, then 1 minus GF, because F is 1 over G, this is going to be 1. 1 minus 1 is going to be 0. So it means what? If I can choose my F to be 1 over G, then regardless of what input I'm passing to the system, I can always have what? 0 tracking error. So my system can perfectly track any type of input as long as I can choose F to be 1 over G. Now let me talk about this F equal 1 over G for a second, and then we continue. So in the previous video, if you remember, our G was what? It was 1 over M effective times S squared plus B effective times S. It was a second order type 1 system. So from here, your f, which is 1 over g, is going to be what? It's going to be m effective, s squared plus b effective times s. So it's not going to be a second order system. It's actually not going to be a physical system. It's going to be a first derivative and a second derivative combined. And there is no physical system for which the dynamic is shown by such behavior. Okay, in a physical system in general, if your g is like numerator over denominator, the order of the numerator polynomial is always what? Less than denominator. So if you write this as like a was 0 plus a1s plus dot 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 plus ams to the m, and for denominator you go with like b naught plus b1s plus all the way to bn times s to the n. For any physical system, m is to be less than n for what we call a causal system. And causal means the input at the moment and in the past is creating the current output. If the system is not causal like this is a non-causal system, then it means the current output is determined by future input, which is not what you see in the real world, right? The current position of any system is always determined by its past and current situation, not by its future. So that's why even when you go in Matlab and you want to use a, let me show you, you want to use a block diagram of the system and you use the transfer function. When you pass to it the numerator and the denominator, I just told you, it is not going to like it. So if you go and say, let's say here, I want to create a blank model, then you go under the continuous and you try to define a system like this, as I said, which you're going to see, by the way, down here. That's what I said. If you want to create this in MATLAB Simulink, it does not allow it. So if you want to create it, you have to use the derivative block. And we're going to talk about it in a minute when we go to Simulink, because I have a Simulink demo to show you. But just wanted to tell you that this feed-forward block is not going to be a causal system. Now, moving forward, in our case, in the previous case, we showed that the system is capable of perfect tracking for any input, but remember, in this case, in the previous case, all we had was one single input R. In our model, for a specific joint control, not only we have this R, which is your Q desired, right, the value of the Q that your joint is supposed to go to, you also have what? You also have the disturbance, dk, from the motion of other joints, right? This is your physical model. So in this case, the dynamics of the error is not as easy. If I calculate it again for this case where D is coming, and you again say error is input minus output, calculate everything. Now this time the D is also added to those two previous terms. This time your error is going to be D over 1 plus GH, even if you still choose F to be what? If you choose F to be 1 over G, this is going to be your error, D over 1 plus GH. So with any kind of disturbance, the error is not going to go to what? Perfectly zero. It's not going to happen. Good? Right? So now the goal is this, to choose this feedback such that you minimize the effect of disturbance, but still it cannot do perfect magic, right? So the method of computed torque says, well, if regardless of what H I choose and regardless of what F I choose, I still have a non-zero error. This is my idea. Since I cannot get rid of D through selection of F and H, why don't I bring one extra input, call it DD, where this DD is to estimate DK very closely. Because I know how to calculate DK, right? If you look at DK, it is the effect of what? It is the effect of other angular accelerations. It is the effect of the centripetal and Coriolis accelerations, and the effect of gravity. So I know exactly how to calculate decay. So if I can estimate this decay and pass a negative version of that decay, or a positive version of that, because here the decay itself is negative. If I add a positive version of decay, which I call it dd, to the system, is kind of like that dd and that decay already what? Cancel each other. So I go back to what? I go back to this case, where there is no d, there is only r. And in this case, remember, error is always 0. That's the method of computed torque. Try to estimate decay. Here we call it dd. And then what? Pass it as an extra input to the system in addition to feedback and feed-forward. And then guarantee that your system can track any type of QD regardless of how complicated it is. Good? So how do we do it? I told you about what we choose for f. F has to be 1 over g. So if this is g, that has to be 1 over g. That is already determined. For the h, for feedback, we use a PD controller, or we can also use a what? A PID controller if we want. If you still see there is some tracking error going on. So that's clear. And now, how do we approximate dk and call it dd and plug it in? If you look at the formula for dd, it's exactly the same as dk, except for one thing. What is that one thing? The one thing is, instead of calculating dd at q's, it is calculated at qd's. So the q's are replaced by what? By the qd's. That's the only difference between dd and dk. Otherwise, they are exactly the same formula. Let me just copy the formula for dk and see if I can place it right next to this guy for you. So you can see that they are identical here. So as you can see, they are identical. They are exactly the same thing, except wherever you have q, you replace it with q desired. If it's q dot or q double dot, you also do the same thing. You replace it with q dot or q double dot desired. And what does this do? Well, let's look at the dynamics here. If I plug such a thing in the system, what's going to happen? So here, the input to the system, UK, other than DD, UK, due to feedback and feed-forward, is going to be what? Is going to be M effective QD double dot, right? Because this S squared is double derivative. When you apply it to QD, you get QD double dot. Plus B effective times S times QD, which is QD dot, plus KP and KD times the error term. Remember, this guy is the error, this guy is the QD. So QD goes to the DD and to the F block, but the error goes to the H block, right? And now the input to your system, the total input to your system, this guy here, is going to be UK plus DD, and then minus what? DK, which you can see here. Right? Now, what's going to happen? If, when I am close to what? To the goal position. If, when I am very close to the goal position, my Q is going to be what? Is going to be very close to QD, correct? I can do some very good, perfect job of tracking. That means your DK should be approximately the same as what? DD. If that's the case, means these two would cancel each other. So if you replace the same u that you have on the top here in this equation, then you will get m effective qk double dot plus b effective qk dot equals m effective qd double dot plus b effective qd dot plus the kd error dot and kp error. And if I bring these two terms to the right hand side and subtract qd double dot from q dot of k, that gives me error double dot. And if I subtract the b effective qd double dot minus qk, that gives me b effective e dot. And I also have kp. So if I basically rearrange it, the resulting equation is going to be this. That's m effective e double dot plus b effective plus kk derivative. Here we chose k derivative to the k, not k derivative. The amplifier again, we chose it to be 1. So here we can go just with 1 for both of these. E dot plus kp dot e equals 0. And in terms of the error, this is a second order differential equation homogeneous. And the solution of this is going to be e of t equals what? Some initial value of error times exponential of what? The roots of the characteristic equation. Correct? Like negative, for example, if I choose my gains properly, it's going to be like negative omega times t. So my error should exponentially go what? To 0 if the roots of the characteristic equation, which is what in this case? I want you to give me the characteristic equation, is going to be m effective s squared plus b effective plus kd times s plus kp equals 0. Right? If I choose my kp and kd properly, so that both roots of the characteristic equation are equal to negative omega, then this is your solution, right? So here I want both of my roots to be omega, so I want this to be corresponding to what? To m effective times s minus omega squared. If I can say these are the same thing, then from here I can easily also find my what? My kd and my kp, I choose them properly so that I have two repeated roots of negative omega, and it means my error goes asymptotically to 0, converges to 0. Correct? So, and that's not hard, because from here you can see that if you look at the linear term here, the linear term is b effective plus kd. And here the linear term is going to be what? It is going to be negative 2 omega times m effective. And the constant term here is kp. The constant term here is m effective times omega squared. Correct? So clearly, if I have my m effective and my omega, I chose my omega, this formula gives me kp. Then if I go from the top one, my kd is going to be what? It is going to be negative b effective minus 2 omega m effective. Correct? So by choosing your gains properly, or actually here it should be s plus omega. It's my bad, because if your root is negative omega, this should be s plus omega. So this guy should be 2, and that means this should be positive 2. There we go. So if you choose your kp and kd equal to these two sets, just choose omega, whatever you want. The bigger the omega, the faster you converge to 0. Choose your omega, determine kp and kd from here, plug them into your feedback system, Your feed forward is clear. Your DD, the formula for it is given. And guess what? You can assume that your error will converge to 0. Of course, for it to converge to 0, your DD and your DK have to cancel each other. If they don't cancel each other, then which means Q and QD are close to each other or almost identical. If this thing does not happen, your error will not go that clean and perfect to 0. So this method is not going to give you the perfect magical solution by that works under all sorts of conditions. As you can see here, I mentioned that the difference between the computed torque term dd and the actual disturbance is 0 when you are doing very perfect tracking. In reality, the goal is not to make this difference perfectly 0. It's just to what? To cancel as much as you can from dk through what? dd, and to reduce the amount of this non-zero term that you will get on the right hand side. Okay, because when they are not equal, the right hand side is not going to be 0, but you want to make that non-zero term as small as possible. So hopefully you can use a PD, or if you still have, as I said, the steady state error, you might add an integral term also here. That can reduce the amount of what? The amount of error. Now you might say, why don't you add that? Well, we can. One of the reasons that you see in my videos and probably in many other videos or textbook, people don't use PID controllers when they want to prove something is when PD comes in, the proof of convergence, as I'm showing it here, is not a hard thing. You end up with a second order differential equation, and you can choose the roots of the characteristic equation, so you get asymptotic convergence of error to 0. But when the I comes in, now this equation goes to a third order, and then choosing the roots and showing asymptotic convergence is not as trivial. So really the main reason for choosing PD over PID in the books is just due to proof of convergence. But in practice, when the steady state errors that are non-zero show up in my system, I always try to add an integrative component, of course with not really large gains, because large gains of integral component will always lead to instability of the system. So that's one reason, one thing we need to discuss. The second thing is, you might say, well, why didn't you use the components of Q, Q dot, and Q double dot in this computed torque? Why did you use the desired component of Q, D, and D double dot in DD? Because if you use the Q's in the formula for DD, then DD would be identical to DK at all times. And there would be no need for me to assume that Q and QD are close. Well, right, but the problem is, where would you get those components? If I wanted to use my DD the same way, define it the same way as DK is, the question is, you have to have a way to measure these values, right? You cannot just estimate them. Look here, you need Q's, you need Q dots, and you need Q double dots for DK. So if I want to have something like DK hat, which is an estimate of DK, then it should be the very same thing, correct? But this Q double dot J is going to be Q double dot J hat. By the way, this MJK that I wrote for you is not constant. It is a function of Q itself. So it is going to be like Q hat. And then plus double summation, and then Cijk, and then Qi dot hat, Qj dot hat. And then plus G of Q hat again, where hat is the estimate for the parameter. And the question is, where did you get these? I mean, the Q's themselves, the Cijk, by the way, you also know this is also a function of the Q's. So the Q hats can come from your encoders, right? These are the estimates of the joint positions. You get them from encoders. Fine. Where do you get the dot terms? You might say, well, from the tachometers. Fine. What about the double dots? Do you have a sensor to give you angular acceleration? Well, not necessarily. Right? I mean, if it was linear acceleration, maybe you might say I use an accelerometer. You might say here I could do a numerical derivative of the tachometer dot values to get double dots. So numerical differentiation. Right, but what's the problem? The problem is, first of all, the encoder signals, they have noise. Tachometers, they have noise. And when you have a noisy signal, when you take derivative of a noisy signal, it's going to have huge magnitudes in it. You never take derivative of a noisy signal. You always have to filter it first. So you cannot do real derivative. You have to apply what we call a high-pass filter, which is a low-pass filter to reduce the noise and then take a derivative. Okay, and all of those will cause any of these hat values to be quite different than the actual value. So your dk will never be identical to d. It will be just an estimate of d. The same way that dd is. Your dd is also an estimate. Okay, and plus, not always you have all of the sensors handy. Not every control system, every robot that you have, the motors come with encoders as well as tachometers. Many of them come with only encoders. Some of them have velocity feedback, which is the tachometers. Okay, and one other thing that you have to consider is you have to do all of these calculations of all of these hats in real time. As the encoder comes in and as the tachometer comes in, you have to do all of these hat calculations in real time. And that's not easy to do. Your processing of the controller system, the controller of the robot should be very fast. It needs a huge real-time demand of computation. That's one thing. And the other thing that you need to pay attention to is the delays. Not all of the measurements from the sensors, especially tachometers and encoders, they are coming without delays. They always have a delay in the feedback line. So if instead of this Q, you now also have to get what? Some Q dots and send them all in to this brain, the controller, that gives you back what? Q hat and Q dot hat, and then Q double dot hats. This is affected by the delays in communications, and it needs a ton of processing in real time. So estimating dk by a dk hat is not a trivial job. Okay? But dd is not that hard. Why? Because you know your desired Q most of the time ahead of time. This is how I want my joints to behave. Let's say you got them from your inverse kinematics. You have your end effector desired pose, then you applied what? Inverse kinematics, and those gave you your desired joint values. Now that I know my desired joint values, ahead of time I can do my differentiations, and ahead of time I can get my QD dot and QD double dots. And when I have that offline, not in real time, I can calculate all of the DDs that I need for my entire motion. So that's the advantage. DD can be calculated ahead of time, offline, not in real time. Okay, and it is going to give you an estimate of dk the same way that dk hats does. Now I know in many control algorithms we do use a dk hat. That could be an alternative approach. But the goal of whether dk hat views or dd is to cancel the effect of what? Dk to the best of our abilities. We will never perfectly cancel it. We just reduce it to some small magnitude that hopefully now our PID controller can handle and bring it down to very, very small numbers or zero. Okay, so it's a combined effect. Now, you see here, I also mentioned that DD compensates the nonlinear coupling inertials, Coriolis, centripetal, and gravitational forces. That's the goal of that to the best that it can do. And I mentioned that you can do many of these computations of DD in offline, not in real time. And I also mentioned when there is a non-zero error, you can use a PID instead of a PD. So I covered all of these topics. One other terminology I want to show you before we go and look at the demo is we call feedback linearization. And that is exactly what we are doing here. By adding another extra term into the control, I'm trying to get rid of some of the nonlinearities in the system, and dk is the largest nonlinear term that we deal with in the system. Because if you look at the blocks here, the F block, the H block, and the G block, all of these are linear systems. We could apply a Laplace transform to them. The big nonlinearity that you have is dk, and by bringing dd, you want to cancel that nonlinear term and make everything linear. So that's why we might call this method one specific case of a general category in nonlinear control we call feedback linearization. This is one of the most common methods in controlling nonlinear systems, and a robot is a nonlinear system. So one of the most common methods of nonlinear control is called what? Feedback linearization, and that's what you're doing. Now, it's not perfectly linear feedback linearization, because this term here, this DD, is not generated through feedback. It is directly generated through QD. It's not generated through QK or Q dot K. If I use this DK hat that I just mentioned for you, this dk hat is generated through feedbacks of encoders and tachometers. If I use d hat k instead of dd, then that's perfectly what? Feedback linearization. Okay, so this is one of the most common control methods for nonlinear systems. Okay, so hopefully this is clear. And again, we call it computed torque because this dd are the torque. By the way, the unit of this dd is torque. If you look at the unit of that, it is like Newton meter, or it is like pound force times feet. Okay, if you look at each and every one of these terms, they have units of torque. So we call it computed torque, and we can do pre-calculation of them. Okay, so now that I explained the method and the logic behind it, why we add a feed forward, why we add a computed torque DD and everything, let's go ahead and look at a Matlab demo that I wrote for you. So this is my Matlab demo for the 2 degree of freedom planar arm. These are the robot parameters. These are the gearbox parameters, the DC motor parameters, the M and B effectives. My goal is to end up at 60 degrees and 45 degrees for link 1 and link 2, starting from what? 10 degrees and 18 degrees. I'm using the same numbers I used in my previous video. And again, I choose some omega. I determine my KP, KD, and KI. Here I am using some I term. I run my Simulink model, get the data from it, and plot it for you. And this is my Simulink model, which is similar again to the previous video I published, except in the previous video I did not have the DD term. This time I do. So I have this extra blocks added, as well as these F systems, the feed forwards, which are M effective S squared plus B effective S. And as I told you, when I want to make that non-causal system, I cannot use a transfer function. I have to use 1 and 2 derivative blocks. So by no means here, you can go ahead and say, hey, I want to go to continuous system and I want to use a transfer function. And when you do so, then come here and in the numerator, type in, let's say, M effective 1 and B effective, right? And 0, so it's M squared plus BS plus 1, and then the denominator is just 1, number 1. You cannot do that. You see, when you do it, it says the time domain realization of the system is not going to be possible. It failed. Why? Because the system is non-causal. It says the order of the numerator ought to be less than or equal to the order of denominator. Here, your numerator is order 2. Your denominator is order 0. Okay, so you can never use a transfer function. Okay, it's not possible. The only way you can create such system is using the derivative blocks. Just wanted to tell you. And now here I'm going to run the code and show you. And this is what we have. The dash dotted line or the dash line in black are the desired values for Q1 and Q2. And the blue and the red are Q1 and Q2 themselves. You see both of them had some overshoot, and now they are trying to exponentially get to what? To the final value. And if you look at the final values, look at basically the steady state error, you see that the steady state error is almost 0. It's not going to be like perfectly 0, but almost. And if you look here, you see the difference between the desired and the actual signal is what? If you see, they are the same until what? 4 digits almost. So up to 4 digits, they are the same. So the error is of order 10 to the negative 4 radians. It's very, very small. And if you, that's for Q1. And if I show you Q2 also, you see some error, but it's not, again, super large. If you see here, it is of order 10 to the negative 3, I'm sorry. The third decimal is different, almost, or less than that even. Because if you can see, the order is less than 10 to the negative 3. Okay, so you see they are adapting very well. And although I use the PID control and everything, and although it's still set point tracking, the desired values are constant, the error, the steady state error, is not perfectly 0, but it's so small. When it's 10 to the negative 3 or 4 radians, remember each radian is 57 degrees. So 10 to the negative 4, it's what? It's basically 5 over 1,000 or 6 over 1,000 of degrees. Or this one is 5 over 100, right? 0.05, 0.06 degrees. So both of the errors are less than even 0.1 of a degree, right? Which is even your encoder cannot probably measure. So practically, in practical world, these guys are what? Almost settled exactly. And the good other thing is you don't see overshoot, undershoot. You don't see oscillation. You see kind of like a close to a critically damped response, although you do have one overshoot. But it's not overshoot, undershoot, overshoot. There is no oscillation. It's just a one-time jump. So the system is behaving very well, and I can change my omega to change the response. Remember, in reality, there is saturations here. And if you apply saturations, the system will never behave the way it is. It is going to show you some big variations, big oscillations in the response. So in reality, the saturation is what limits the power of your control system. Okay? How much amps, how much voltages you can draw out of your controller or its power sources. So hopefully this video was useful to you, and I will see you in my next video. Thank you.